Hi, my name's John Ferncombe. I'm a test engineer here at Zipp Speed Weaponry. We're in Speedway, Indiana here in our test lab, and we're taking a look at some of the things we do to our wheels to test them out and verify our designs before they ever reach the market. At my right is our latest version of our drum tester. So our tester is based around a 32-inch diameter drum that's 36 inches in length, weighs approximately 960 pounds. And we can do these tests anywhere from 0 to approximately 54 miles an hour. As you can see, we're set up for 3 wheels at a time. Generally speaking, we do test 3 wheels simultaneously. And there's several different tests that we run on this drum. Black, flatter bumps with chamfered edges are those specified in the DIN standard, so it's a much shorter bump that's also a little wider. It's approximately 2 inches wide. Whereas the blue bumps that are triangular in cross section, those are about 3/4 of an inch tall and have a 45-degree chamfer from their peak. So those we use to simulate some of the more rough cobbled sections and things of that nature. You can see some of these are vertical, and right now the one closest to me is actually at an angle. We can test at plus or minus 10 degrees, so simulating prolonged cornering. So for example, on a rear wheel where we have some different hub flange geometry, we can kind of investigate some of the different lateral stresses and see if we're generating any failures that way. And then we can also do a test that we call either the Cancellara test or the Thor test, in which we can actually simulate an intense sprint or hill climb effort and actually oscillate the wheel back and forth plus or minus 10 degrees as the test is running. As I mentioned before, the old DIN standard is 6 hours at 12 kilometers per hour surface speed. We started testing that way initially, but found that we could run for literally weeks at a time and not break anything. So we've modified that protocol, and now we run at a speed of 40 kilometers per hour, which is not quite 25 miles per hour. And we'll run typically a minimum of 40 hours before we start to see spoke nipple or spoke failures. And at that point, we'll replace either the spoke nipple or the spoke as needed and continue to run the test until failure. That's the key thing, is we need to generate a failure of some sort, otherwise we're not learning what we can do to improve our product. So that's the key thing. We'll run it as long as it takes. Typically it's a week to 2 weeks, even at those accelerated speeds. And that's one of the nice things about where we are, where we're doing all our manufacturing in-house and all our testing in-house. We can iterate through a design typically in a matter of days when you're looking at accelerated fatigue test in conjunction with some of the other testing that we perform, so we can quickly determine if a new laminate or new material is improving our design, not changing it, or actually making it worse. So now we're at our impact test machine, which is a rather crude looking machine, but it's actually something that's shockingly consistent in terms of repetitive failure modes. It's a machine that we use to induce failure modes that we see in typical real-world failures. So what we have here is a bunch of weights on our impact sled, and then we have a couple different shapes that we use here to simulate various types of impacts, from potholes, cobbles, curb impacts. As you can see right now, it's set up to impact the wheel basically top dead center. So what we do here is we'll start our impact test. We fixture the wheel in place. We have an inflated tire, as you can see. We have a known mass here, gravitational acceleration, and the height at which failure occurs. So what we'll do is we'll start this at 8 inches above the surface of the tire. We'll drop it initially from there, and then we increase the height, dropping again on the same location, and we'll take that to failure. Now we're at about 16 inches above the surface of the tire. We're to the point where typically we'll start to see some other wheels on the market start to fail. That's been one of the things, as we were developing the carbon bridge technology for this wheel, we went through approximately I believe the last count was about 140 different laminate revisions, and now we're to the point where nothing is as strong as this wheel at any comparable weight. So here we'll take a look at the type of impact that this wheel will have no problem with, while others might not. So now we're at our braking performance tester, and what we've got here is a machine that we've set up to test a variety of components of a wheel and also address various brake pads. We've had our brake pads on the market since 2003, and we're always looking to evaluate new potential brake pads and see how they perform and also how they affect thermal dissipation and overall rim longevity. So what you're looking at, we have a wheel it's driven through the freehub body. It's coupled on the other side to a rather large flywheel. It's about a 189-pound flywheel that we can spin anywhere from 0 to not quite 50 miles an hour. And basically the intent of that system is to simulate a 195-pound rider and bike descending about a 12% grade at those speeds. While we're doing all that, we're taking a variety of data as well. We've got the brake caliper is mounted to a little sled up here, and we've got a dynamic load cell up here that gives us data for the braking force. And then up here where the cable is pneumatically actuated, we've got another load cell that gives us data for the cable tension. And both of those are very fast responding load cells, which enables us to see when we start to develop any pulsation. That's something you can see as you start to get rim heated up or certain brake pads as well. They'll start to leave little deposits on the surface of the rim, and that's something we'll be able to detect with each of those load cells. These two guys up here are some direct contact thermocouples, and those we actually embed in the brake pads, and those we use to keep track of the brake pad temperature as we're executing a test. Also over here we have some non-contact thermocouples that we use to monitor the temperature of the rim. So we're able to use those and adjust those for various emissivity constants that are reflective of different surface treatments, different rims. So just ensuring that we're getting consistent and accurate data across different rims that we're evaluating. So I can go ahead and start this up, and we'll have a look at what exactly we're doing here.